Okay, so we are starting with the topic of electrical working, which is 4.2.5. And so what we're going to talk about over here is power in electric circuits. So we've talked about power in an earlier chapter back in Unit 1. And power, the definition stays the same. It is work done in unit time. Oops, work done over time taken, or it is the energy transferred over the time taken. Right? And so why do we need to know this? Because it is important to know the rate at which electrical current transfers energy from source to the components, the circuit components. Right? So it's important to know the rate. Why do we say rate? Because we're measuring work done or energy transferred over time taken. So that gives us a rate, which is basically power. The rate at which electric current transfers energy from the source to the components. Right, and so over here we've got power equals to work over time, right, or energy over time, and this gives us joules per second, or the watt, also given as a W, a capital W, not to be confused with work. Okay, now
Yes.
let's do some uh,
Questions?
some gymnastics.
Okay.
Okay, so if we have P equals to W over T, earlier on, I'm not going to flip back, but if you recall, we found that work is right done when a steady current, when there is a steady current for a particular time in a device with a certain potential difference. And so we came across the equation W equals to uh, I into T into V, or I think I wrote it as V into I into T. Same thing, right? And so this is one of the equations we actually can, if I actually just backtrack, maybe it will help jog our memories. Right, so over here, okay,
Yeah.
so all of this, whatever we did back here, right, and so we ended up with W equals to VIT or ITV, however you want to say it, so same thing. And so you've got this, and so if we plug this in to power equals to work done over time, and that is I into T into V over T. And so what's going to happen is, right, T gets cancelled out. And so you end up with P equals to IV, which is current times voltage. Let me just write that over here. So again, now you've got a way of moving things around depending on the kind of information you have. You have the work done, you have the time taken, or the energy transfer and time taken. You can do the calculation, apply it directly. If you don't have that, right, you can use the current and voltage. Okay.
Yep.
Okay. Now that's not where the gymnastics stop,
Wow.
right? Uh, the second equation is, right, P equals to E over T. And so if we rearrange that, E equals to PT,
I
right?
think this is just shuffling depending on what the subject is, right?
Yes, but that shuffling is something that you need to be familiar with. And so we get IVT again, right? Which is basically the equation for work done, right? W equals to IVT. So we know that work and energy transfer is the same thing. They're both in joules, right? So not surprisingly, we got the same thing again, just as work we substituted over here. So, right? Not surprising. Expected, in fact. So to calculate the power of an electrical appliance, we multiply the current by the potential difference. For example, right? Let's say we have a device, we have a lamp of 240 volts, right? And we have a current of 0.5 amperes. And so what's the power? It is 240 times 0.5. Oh, sorry, 0.25, not 0.5. And so what would that give us?
Right. 60?
Yes. So we're going to get 60 watts out of that, right?
Yeah.
Which means that, right, the circuit or the source, right, is transferring 60 joules of energy per second. So 60 joules of, like, joules means energy, obviously, are transferred to the device. In this case, it's a lamp, every second. Okay.
Yes.
And so, right, that is for watts. So you can have larger units of watts, right? If you can measure things in kilowatts, and so that is 1,000 watts. If you got something like 60 kilowatts, that is 60,000 watts. And then you can have something, the megawatt, 1 megawatt, that is a million watts, right? And so for example, you've got like 500 megawatts, right? And that is the power supply, the power generated to supply cities and everything. And so that basically means you've got 500 million. That's not 5 billion, you're missing a zero. That's 8 zeros, so 500 million watts, right, of
Yeah.
electricity. So far, so good.
Yes.
Excuse me. Another thing they go on to state is, right, the watts, which basically means the power, is amperes, which is the current, times the voltage, which is the volts. And so you can rearrange this and say the volt equals to watts over amperes. And so they use this to define what a volt is, right? And so they say the volt is the watts per ampere, right? Which is used to, give the potential difference.
Yes.
Okay.
Can we do more questions?
This was just a, a question given in the text itself, right? Let's move on and see. They do have a work example, so we will try those. So before that, another thing that they're saying is if all the energy is transferred to thermal energy in a resistor, so if all the energy is transferred to thermal energy in a resistor of resistance R, right? So there's giving like the symbol, obviously not a value to it. Then V equals to IR, so that's Ohm's law, and the rate of transfer of thermal energy so when you're talking about rate of transfer of thermal energy, they're talking about what? What's the rate of transfer of energy? You guys there? Let me just go back. What is rate of transfer of energy? So as you can see on screen, the rate of transfer of energy is power. So what they're basically doing is they're doing, so in case, right, you are dealing with resistance, and so how can you find power when you know resistance and not voltage, right? So P equals to VI and V equals to IR, and so P equals to I R times R, which gives you I R squared, right? And so you can find the power when you don't know the voltage but you know the resistance.
Okay.
Oh, sorry. I wrote that wrong. Not IR times R, but IR times I. Sorry, my bad. IR times I, and so that becomes I squared out, not IR squared. So in any case, you can find the power when you don't know the voltage, you know the current and the resistance. So there's a way to do that as well. Okay. Now, right, we can obviously move the equation around even further, right? What if you don't know the current? And so P equals to VI and I equals to V over R. And so P equals to V multiplied by V over R, which is giving you V squared over R. So you can find power in any case. You can find power directly when you know the current and the voltage. So P equals to IV or VI, however you want to say it, right? Or if you don't know the voltage but you have the resistance, you can still find it. If you don't know the current but you have the resistance and voltage, you can still find what the power of a component is. All right. So what this tells us, that if the current is doubled, right, the power is 4 times as much. So if the current is doubled, right, the power is 4 times as much. Now, Sobia, you were asking for some questions. Are you there? So we have a question. You've got a lamp of resistance 12 ohms, and the current flowing through it is 0.5 amperes. So I equals to 0.5 amperes. And the first thing they're asking you is what is the potential difference, right? Or the voltage. And so we know V equals to IR. And so that's giving us 0.5
Multiply with 12.
into
That will
12,
give you 6.
6 volts.
Yeah.
The next thing, right, they're asking you for power. And so we know P equals to VI, which is 0.5 times 6, which is going to give us 3 watts or joules per second. Right? And then they're asking how much energy is transferred to the lamp in 6 seconds. And so you know P equals to E over T, and therefore E equals to PT. And so we don't need the VI and everything, we've got this, right? And so that is 3 into 6, which is 18 joules of energy. So in this case, we don't need to do, oh, P is this and then VIT and all of that stuff. We don't need. We have the value of power. We just put it in directly and we get our value. Okay.
Yep.
Okay. Now something simple enough to wrap things up. The first thing is a joule meter.
Okay.
And so this is a device uh, that can be used to measure the electrical energy directly. Okay.
Yes.
So instead of using like connecting an ammeter and a voltmeter and then getting the power and then the energy value and whatever, there's a device called the joule meter that can be connected directly and it measures the energy directly. right? So obviously it detects the voltage and the current and everything and does the calculation and presents the energy as directly on display.
Okay.
And then they're talking about commercial or energy supply and paying for electricity, paying for electricity. And so obviously electric supply companies, they charge you for electricity. And in that case, right, if they're going to charge you per joule, that's a very small amount because they are supplying in like, right, uh, huge numbers. And so what they have is a unit called kilowatt hour. Oops, single L, kilowatt hour, and it's given as kWh. So W is capital, K and H are lowercase. And so that,
That's the SI unit for it, right?
huh?
That's the SI unit for it, right?
That's not the SI unit. That is the symbol. Yes,
Yeah, okay.
right. And so what kilowatt hour means is 1 kilowatt of energy used by an appliance in 1 hour. Right. So that means 1 kilowatt energy used in 1 hour, and this is generally referred to as 1 unit of electricity. Right, so if in your electric bill they're like these many units have been used, that means these many kilowatt hours of electric energy have been used. Okay, so
Yes.
how do we break that down, right? 1 kilowatt hour, so that's 1 kilowatt, so that is 1,000 joules per second, right? 1 kilowatt times an hour. So if we convert an hour into seconds, we get 3,600 seconds, right? And that gives us how many joules of energy? That gives us 330, right? 3,600,000 joules. Am I reading that correctly? Yeah. Or in other terms, 3.6 megajoules of energy. So that is obviously easier to do, to handle, as opposed to you know giving you a bill saying that you've used these many million joules, and you're like, oh my god, I use so much. Like, yeah, you probably use a lot of electricity, but it's better than it's better saying that you used 400 units, meaning 400 kilowatt hours of electricity, as compared to saying 3.6 times 4 is what, 12, and somewhere like 15, 16 million joules of, right?
Yeah.
Okay, so a 3 kilowatt electric fire, for example, and it's working for 2 hours, and so that would give 6 kilowatts, right? Obviously, and so that would be 6 units of electricity that were used. And so whatever the unit rate of electricity is, you'll be charged accordingly. And so the electric meters that are used uh, at residence or commercially, right, they're joule meters, and so they give a direct reading of this much energy used, so these many units used. Okay.
Yes.
Yes, Sarah,
Yes.
you were saying something.
No.
Okay. Okay. Yeah, and that brings us to the end of the chapter. Right, next up is actually unit 4.3. So we'll leave that for next time, where we're going to start talking about electric circuits. Any questions?
Yes.
No.
No.
Yes, no?
No.
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 All right. See you next time then, inshallah.
Inshallah.
Okay
Allah
then.
Hafiz.
Allah Hafiz.
Allah Hafiz.